are subject to the same SN and the same BN. So that's one of the assumptions. Whenever you're building models, you're making these kinds of assumptions because individual variation can't be taken into account because it's impossible to know what the potential of each individual is. It's like me coming in and saying, you're going to have 2 kids, you're going to have 1, you're going to have 3, so on. How could I possibly know this? And this is the thing about one of the mysteries of saying the fitness of a group. The fitness of a group is a sampling problem. If you say this group of individuals is fitter than that group of individuals, then you say on average each individual in that group is going to reproduce more than an average individual in that group. But you can belong to a very fit group and then walk out in the street and be knocked down by a car. 0 for you. So this sort of brings into what we're going to do later, which is called stochasticity, where we take into account that everybody is subject to some stochasticity. So we're all like coins being flipped. And the only thing we can say about us in terms of coins being flipped is that if there's a group of us, we all represent the same coin, and so we know on average what's going to happen. So we've got a group of 1,000 people, we know that everybody in the group on average is going to have 2.1 individuals per individual in terms of reproduction, or is going to live on average so many years. But there's that incredible variation. And this variation that comes in is called demographic stochasticity. Called demographic because it's got to do with the demographic parameters like births and deaths. You know, how many individuals, how many newborn will you have? Are you going to survive the year? It's not about are you going to survive the year. You know, all individuals like you, what proportion of you as a group do we expect to survive the year? Yeah.
So is there chaos
No, it looks like chaos, but it's exactly the opposite of chaos. Chaos was deterministic, and that is you could exactly calculate what was going to happen next, only that when you finish calculating and you have a look at what the numbers are, they didn't make any pattern. You know, they didn't go to equilibrium, you didn't get a cycle of 2, you didn't get a cycle of 4, but it was exactly calculated. Stochasticity is the opposite, is that I can't calculate exactly what's going to happen, but what I have to do is I have to either flip a coin or throw some dice. I have to generate a random number that will tell me something about you. So for example, if you have a probability of 0.7 of surviving a year, will you survive or not? If I can draw a random number between 0 and 1, and that number is less than 0.7, it'll tell me that you're going to survive. If it's greater than 0.7, it'll tell me you won't make it. So the way we generate stochasticity in a computer is we draw numbers at random from a computer between 0 and 1. And computers have ways of giving us these random numbers. And we're actually going to talk about this in 3 or 4 weeks. And the ways that it has to do this, I mean, it's counterintuitive in the sense that computers are not stochastic machines. They're exactly deterministic. They calculate things precisely. So how does a computer come up with a random number? And in fact, it can't. It can only come up with something called a pseudo-random number. Looks like a random number. Unless it's doing something truly random. So when physicists want to get random numbers, they have little Geiger counters. And they say, okay, this Geiger counter is going to count the number of radioactive particles, cosmic rays coming from the universe outside over a period of time. And that's a truly random number. And then it takes that, and it uses that to generate a number in the computer. So it counts things. So sometimes computers will go and look at clocks, which are not truly random, but have a value that is not repeatable, and they kind of use that to generate random numbers. So we will be talking about that towards the end of the class. And we'll talk about it in the context of using Leslie matrix models like this to calculate whether species are going to survive. Because, for example, if you've got a small number of individuals, 15 individuals in a population, you say, what's the probability that it's going to survive? Well, under one set of scenarios, there may be a lot of good luck events, and the population starts growing rapidly. It's the same with Ebola. For example, there's one case. So one case comes into the United States, and you say, is there going to be an outbreak, or isn't there going to be an outbreak? Now, if the Ebola model has the equivalent of what we call this dominant eigenvalue greater than 1, then the number of cases is going to grow. So we make disease models like this, where you also look at what's called R0, which is the dominant eigenvalue, the net reproductive value. Does each case cause more than 1 new case or less than 1 new case? So if a case coming in has a probability of only causing 0.9 new cases, then that's good news. But if it has a probability of each case causing more than 1 new case, then that's going to grow. But what might happen is you get 3 patients, but nobody passes it on. Or you get 3 patients and happens to pass on to 2 individuals. Or you get 3 patients, and each of those patients passes it on to 1.6 or 1.7 individuals, so that a couple of weeks down, you now got 5. And a couple of weeks down, you now got 8. And so then you get the result, like you saw the CDC projected that there are going to be 1.4 million cases in February next year. Who saw that projection? Kind of worst case scenario, yeah. How did they do that? Well, they looked at the current caseload and what's happening, and they said approximately every 26 or 27 days, the population of the number of cases is doubling. And so a doubling process is a fearsome process because there's this apocryphal story about the guy who introduced chess. He invented it, and the king was very pleased. So he said, go get this guy in. And when the guy came in, he said, I'm going to give you whatever you want. What is your wish? And the person who invented it said, well, on the first square you put 1 grain of rice, and on the second you put 2 grains of rice, and then on the third you put 4, and you double up until you get to 64. And the king said, but that's ridiculous. I want to give you something more than that. So the guy said, no, that'll be enough. And then when the king finally did the calculation, there was more rice than there was in the world. So 2 to the power 64 is a huge number. So if a population is doubling every 28 days, then within a year, it's going to be outrageously huge. So fortunately, well, not fortunately, at some point, they're going to actually run out of people. So let's hope it never gets anywhere close to that. But as it seems, the probability of Ebola being transmitted to another individual can go down if everybody changes their behavior. So when the outbreak started, people were sick, and they would go visit their sick friend or mother tending to a child or whatever, and they would nurse them, and they wouldn't take any precautions. Now, as soon as somebody gets sick, you take them to some kind of facility and you isolate them. So if you don't have any isolation, the population, the number of cases could be doubling every 2 weeks. But once you get isolation, then what you've done is you've taken the dominant eigenvalue and changed it from a value that's much bigger than 1. In this case, for Ebola, it's around 2. And you've reduced it to something like a half. And if the number of cases, so if there are 8,000 cases now, and they're halving every month, then that's really good news, because then there's going to be 4,000 next month, only 2,000 the month after, 1,000 is going to die out quite rapidly. And so what is needed is to change the behavior so that the transmission changes. And so it's the same with conservation biology. if things are really bad so that each individual female is expected to produce less than one female, what can you do to improve the situation so that each individual female can now produce more than one female? And maybe that you have to do supplemental feeding, you have to make the environment more favorable. There are various things that you can do. So, for example, in the 60s and 70s, they were putting a lot of DDT into the environment in agriculture. And what that did is eggs that were laid were very thin and they would break. So if you take DDT out of the environment, then again, you can turn that around. So what you're doing is you're taking the S0, and if DDT is there, S0 is small. The proportion of individuals that hatch is small. And you've got to increase S0 to the point where the dominant eigenvalue lambda is greater than 1. So that's how you turn things around. That's why you study these things. Okay.